Hi, this is Linear Algebra section 1.5. We're going to start with question 5 and keep pushing until we get to the very last one. Okay, so I already sort of wrote the questions down, and I'll tell you how I come up with an answer. It's not too difficult, but nonetheless. So it's a horrible graph, but it's a horrible way of displaying it, but I thought this will be best since you can see everything happening at the same time. So this is 5A, and this is 5B, and this is 5C. Maybe I should write that down. A, B, and C. And you guys can sort of see that. So, okay. Essentially all we're trying to figure out is, well, we're going to be given some kind of elementary matrix with some work done, but only through a singular process. So for example, typically if the matrix is, let's say 1 0 0 0 1 0 or 0 0 1, right? So if that's the case, then I use row 1, and then maybe I times it by half and add it to the third row, right? So the important thing is I've only made change once from the original elementary matrix. If you do multiple changes, then this concept cannot apply. So, but nonetheless, so bear that in mind, right? Which is a reason why if you look at all your E matrices, they're really similar to the original elementary identity matrix. So because only one change was made, very difficult to make things very complicated using one single change. So anywho, so let's look into it. So yeah, this is your E matrix, and this is your A matrix, which is the main function you want to work with, right? So what is happening is so if you look, so basically the question is asking, if you do E times A, what would I get? This is what you would get, but let's talk about how we got to that point, right? So if you look at the element, so if we know that if whatever matrix you have, if you times it by the identity matrix, it will stay the same no matter what, right? So bear that in mind, and then look at E. E, it looks like a matrix, identity matrix, but it looks a little off, and we have to figure out what that is, right? If you notice it carefully, it says 0 1 1 0. That looks really similar to 1 0 0 1 we would typically see in identity matrix. So what I would imagine is that the first and the second row were flipped, right? Which makes sense, right? So if that already tells you what this gonna be. So if you look at the regular A matrix, right, that is being multiplied with, we can safely say, oh, so since in the E matrix the change was line 2 to line 1 switch, right? That's gonna happen the same with these with this A matrix, right? So because of that, our answer looks exactly like A, but the line 1 and line 2 has been flipped. That's all there is. Nothing too difficult, right? Now, this does not apply for general multiplications with matrices. It only works for this specific E matrices, right? The E matrices are the ones where, like you have an identity matrix and made only singular changes. Singular change, so to speak. If you look at the letter B, same idea, right? We have this A function, right? And this is our E. 3 by 3 matrix, so it should look like 1 0 0 0 1 0 0 0 1. But something is off. It's at -3. So what singular change we have made to get to this new line, to this new third row? Well, the easy way to look at it is well, in the row 2 is the one with the leading coefficient on the second column. So I'm just gonna times it by 3 and times it by -3 and add it to the row 3. That way it gives you -3, but it doesn't touch anything else, right? Because for row 2, there's 0 and 0 on the first and third column. Therefore, which explains why the third row, column 1 and 3, they are not changed, unaffected whatsoever. Only the second column changed. So that's one of the ways to kind of get a better sense of what is happening, right? So if that's the case, then I can tell. So the change is going to be just right here for B, row 2, 3 minus, this is atrocious. So if I have negative 3R2 plus R3 gives me our new R3. This is for B, right? So if that's the case, then I'm going to do the exactly same thing to the original function. So let's see, focus on the line 2, right? Times it by -3 and add it to the second one. So let's see if that actually gets our answer. -3 times 1 is -3. And I wrote this wrong. Yeah, I was wondering, well, how did you get a 9? But anyway, so yeah, I wrote my answers wrong. But nonetheless, so it's going to be, what was I saying? Yeah, so -3 times 1 is going to be -3, plus 2 is going to be -1, right? Which makes sense. 0 times -3, -3 times -3 is going to give us 9, plus 0, so it's going to be 0. And you can check the rest of the entries to be sure. But, you know, nonetheless, that proves the point, right? So that is B, right? And we can apply the same concept for C, right? So if you look at it here, 1, 1, 1, hey, it looks pretty awfully, you know, it looks pretty similar. But if you look at the first row and the third column, hey, this is 4 doesn't belong in the identity matrix. So that must have been the change that was involved, right? So how do we affect the third column? Well, obviously by only using the third row, because third row is the only one that actually can make any differences in terms of its third column, right? Because its leading coefficient is in the third row. Third column. So, okay, so how do I go from 1 and make it into 4? Well, that's pretty easy. If you do 4 times R3 plus R1 gives me the new R1. That's for C, right? So if that's the case, then okay, that's pretty easy to deal with. So let's look at this one. So the third row times 4, so 3 becomes 12, plus 1 is going to be 13. 6 times 4, 24, plus 4 is 28. Rest of the rows stay the same. So again, so this wasn't supposed to be a hard question. Yeah, but basically this is what 1.5 is sort of all about. And this actually gets important when we try to find inverse functions that are bigger than 2 by 2 dimension. Alright, so on to question 7. Basically, we're sort of doing what we've been doing with question number 5, though the only difference now is instead of trying to figure out what the new function is using the E matrix, now it's the other way around. We're trying to figure out what E matrix is after knowing what the original function and what the new function is going to be. So here's a good example, 7a, right? So don't misunderstand. This is not matrix E. I wrote it as an identity matrix. I'll tell you why later. Okay, I just put it in this form. But let's concentrate on matrix A and B for now, right? So these two are just given from a textbook question, right? So they have from A to F, right? So A, this is matrix. This is the matrix A, matrix B, and then C. We have this A and times it with some unknown E matrix, right? But the result is this. So let's look at what happened. Remember, E matrix can be only singular change, right? So let's find out where the change has occurred. So let's look at the first row. 3, 4, 1, 8, 1, 5. Oh, wow, okay, so something really changed, right? So something to do with row 1, right? Something happened to this guy. Let's find out what actually happened. Let's look at if anything else has happened. It shouldn't have, but let's just double check. 2, negative 1, negative 1, 2, negative 7, sorry, 2, negative 7, negative 1, 2, negative 7, negative 1. Row 2s are solid. 8, 1, 5, 3, 4, 1. That is weird. So that's another change right there. Row 3. Okay, so now, yeah, this should give you a red flag. Because, wait a minute. I thought the whole point of having E matrix is so that you have one singular changes. It seems that two things have changed, right? So that's supposed to be impossible. So the only possibility that I can think of where you can make two changes but still require one move to make that happen, if you flip this first row and the second row. That's the only possible way. And it's just coincident, and and it's not coincidental at all. The third row, 8, 1, 5, happens to be right there. And the first row happens to be right there. So if you found that pattern, good for you. We don't even have to do any matrices. We just could say, we'll scratch that and just say, R1 and R3 has switched. That's all there is. Now, this is supposed to be what the E matrix will look like if there are no changes. Now that we know the first row, that looks really horrifying. So now that the first row and the third row, the third row and the first row and the third row has changed. If there were no changes in the beginning, but now that we know these changes, we can say, oh, the first row and the third row changed. So I'm actually gonna get the first row and the second row changed. See that? So I just moved the third row to the first row and first row to the third row. And that's all there is. And I already found out what the E is, which is what the question is asking, right? So if you actually, if you really have the time, you could just multiply them together and you should get exactly that, right? But the whole point of using with the E matrix is so that we don't have to go through those changes. Once we know what the changes happen, then we can just implement that change on the E matrix ourselves. There's another way, if they bother to ask, they could say, well, let's say it wasn't an E matrix. Well, actually, it is an E matrix, but let's say you can't use that method. You have to use inversion algorithm, right? So we are going to get to that, which is what we're going to be doing in the other questions. But essentially, the inversion algorithm just simply means, remember the inverse formula that we use for 2x2 matrices, right? 1 over determinant, which is AD minus BC, and then you have a matrix where A and D are flipped and B and C are not flipped, but their signs flip, right? So remember that, right? So it's sort of like that, but it's for 3x3 dimensions and beyond, right? So because we can't really do AD minus BC when there's when we're dealing with 3x3 matrix, right? So because of that, there's this. Well, okay, I might as well show you how you. No, I'm gonna save it for later. I will bring that up. Yeah, you know what? Let's damn it. Okay, I want to do it now, so let's just do it. Ignore this step if you're not comfortable with this yet. We will do inverse algorithm more starting on question 13. So feel free to skip this. Okay. This is question 7. So essentially the same thing as question 5. The only difference is instead of trying to find out what the new matrix is after multiplying E matrix with some other matrix, right? So now what you're trying to do is to figure out the unknown E matrix after knowing what original matrix is and what the product matrix will be, right? So yeah, that's what I meant when I say inverse, right? So for example, 7a, E times A will give you a B, right? And they give you A and B, right? So this is matrix A, this is matrix B, then this is matrix E. For now, what I would recommend, you don't have to, but I would just write the identity matrix. For now. This is not the answer, right? So don't put equal signs or nothing or anything like that, right? It's just, I made some singular change to the identity matrix and that will give you an E. So this is a good reference point, so to speak, to start off, right? So anywho, so I'm looking at A, I'm looking at B. There should be a singular change that I should be able to detect. So let's go for it, okay? First one, obvious. Look at the first row, 3, 4, 1, 8, 1, 5. Obviously, they're not the same, so that was a change. So R1 has changed somehow, right? Second row stays the same, so who cares, right? The third row has also changed. Now wait a minute, I thought you said E matrix will just give you a singular change. These are two changes, right? So some people may say that, or some people who are already caught on with just stickers, it's like, let's just get to the point, please, right? But nonetheless, so the only possibility where you have two changes changes that were done with a single step, if those two, if you flip them, right? So what I mean is, so R1 and R3 must have flipped. I mean, because I can't use two different changes to make two different outcomes, right? That's not possible using E matrix. So let's see if that suspicion is true. Well, look at the first one and the third row here. Hey, they happen to be the same. Third row and the first row here, yeah, they're the same as well. So our row switching from R1 and R3 seems like a logical solution, right? So if that's the case, then we can actually look at the identity matrix and say, oh, okay, so we know the change, so let's implement it here to show for it, right? So I'm gonna switch the first row and the third row of the identity matrix. And there we have it, right? So, and that will be our E. So we don't even have to go, do any calculations or anything like that, right? It's that simple, right? Technically, there is another way. This was where I was pondering whether I should bring this up now or later, because technically we do inversion algorithm in question 13. Basically invert. But let's yeah, actually, you know what? Let's not talk about that just now, okay? Then some people are just trying to solve this question. So one step at a time. We will go back to this example later. So the questions are mostly like that. So nothing too difficult, right? So if I have another question, like let's say let's try D, for example, right? So if I try D, E matrix, so this is just my strategy. You don't have to. If this doesn't work with you, it doesn't matter. As long as the answer is correct in the end, that's all that matters. So it's going to be EC equals to A. So that's going to be EC equals to A. So C in this question happens to be 3, 4, 1, 2, -1, -1. No, I'm writing A. Shoot. Okay. So that's going to be 3, 4, 1. Oh, no, never mind. They do look pretty similar. Okay. 2, -3. Yeah. Okay. And then the A is going to be right there, right? 3, 4, 1, 2, -7, -1, 8, 1, 5. Okay. So, okay, maybe we should then put that, or put like this maybe? Because technically they're not equal, right? So, do this on your rough draft, right? Maybe, yeah. But nonetheless, or they have some relations. I don't know what's a symbol for that. But nonetheless, you understand where I'm going with this. So let's look for a singular change. 3, 4, 1, 3, 4, 1. Same thing, row 1 is secured. 2, -1, -1, 2. Yeah, so second row, all good, right? Third row, we see a difference. 2, -2, -7, 3, 8, 1, 5. So, how did 2 become 8? Let's see. Well, there's a bunch of possibilities. You could have done first row times 2 to get 6 and add it to 2, which will give you 8. Or you could have just got the second row, times it by 6, and then add it to the third row. Or maybe you just got the third row and just times it by 4. That's also a possibility, right? So, we could have used the first row, second row, or third row to make this changes. So let's see what is possible, right? Let's get rid of the most obvious outlier out of the way. Timesing row 3 by 3. No, 4, I mean. Right? 2 times 4 is 8, right? Now, would this work then? 4 times -7 is? Nope, that doesn't work at all, right? So, row 3 is out of the question. Now, let's try row 2. I suspect that's not going to work either, but, let's see. So, in order for 2 to become 8, the 2 is here already, so I need to do 2 times 3, right? That way, 2 times 3 is 6, plus 2 is 8. So let's see if that works. 3 times -7 is -21. No, you're right, I'm not going to get 1. So that's not going to happen. Let's try row 1. Seems promising because you're 4 and 7, so if you times it by 2, yeah, it could work. So anyways, let's give it a try. So in order for 3 to become 8, right, I need to make 3 become 6, so 6 plus 2 becomes an 8, right? So if that's the case, I'm going to times row 1 plus R3. And that should give me the R3. But let's see. 2 times 3 is 6, plus 2 is 8, okay? 2 times 4 is 8, -1 is 1. Very promising. 2 times 2 plus 3 is 5. beautiful. It works out beautifully, right? And so if I implement this, this will become this in one single step, right? So so we already noted this changes. Now we're gonna implement the change to the identity matrix so that becomes an E matrix, right? So let's see here. 2 times row 1, so that's gonna be 2, 0, 0, and add it to the third one. So it's just gonna be that. And that's all there is to it. Pretty simple stuff. I don't have, but there are some situations where it's a little bit tricky. So let's actually move to 8. I know 8 is not assigned on the question, but there was one good example where you might have to think a little bit harder. So let's give that a try, okay? Number 8, C, for example, right? So, it's going to be E, B equals to F. Actually, now that I think about it, it's not very different. When I first tried it, I thought it was a little different, but yeah, maybe that's not quite the case. It looks pretty similar here. See, practice makes you do that, right? Right. You practice so much to the point where you look at it as like, wait a minute, this doesn't seem right. So I want you to gain that kind of instinct, and you can't just get that from watching the videos. I mean, watching the video does help, but it does have a diminishing margin of return. So still go to your lectures. Like if I've actually heard a lot of complaints about this too, right? There are some professors where I go to his class, but he doesn't really talk much about the problem. He just talks about the theory, and then we don't make the most of it, right? Still go, right? Still go, and if you can't get anything out of it, just start practicing your problems, right? And after class or whatever, you could just approach him and it's like, I'm stuck here. Could you help me? Or if he's busy, then can we set up another time, right? Just don't use that as an excuse to fail classes. That's when the red flags start to flood in like a hot cake. Sorry, I really need to focus on my problems. Oh man. Sorry about that. Hopefully I can edit this one out, but no promises. F is going to be 815, 811, and 341. Okay, so yeah. So again, so it's the same idea. 815, 2, -7, -1, 341. Let's try 8C. It's not assigned, but it's pretty similar to question 7, so we might run into some odd ones. When I first tried this, I thought it was a little weird, but now that I think about it, maybe it's the same thing that we've been doing in question 7. So, anywho, let's take a look at this, right? So we have B and F, and this is not E, FYI, of course, right? This is identity matrix. We have to transform this so that it becomes an E. Insert any Hannibal Lecter reference if you'd like, but okay, that wasn't necessary. But nonetheless, okay, okay. So yeah, so let's see. First row stays the same. Second row is different. Third row stays the same. Okay, so that's pretty easy. So the 2, -1. So second row is the only thing that's affected. We're gonna try to figure out what that is. The Hannibal Lecter reference really threw me off. Holy crap! So is this the transformation? Okay. I'm being a nerd right now. Okay. So how did we make this change? 2 becomes a 4. So the only way is either this times by 4, but I highly doubt it because there's 1, 1, right? If I times these both by 4, you're not gonna get that, right? So can't use the second row. If I use the third row, 3 times 2 plus 2 will give you 8, right? But let's see if that works. 2 times 4 is 8. Yeah, that becomes 1. 2. Oh, okay. Yeah, that's your answer right there. That's how you figure things out, right? Yeah, so anyways, R3, and I times it by 2, plus R2 gives me R2, new R2, right? Okay, and well, okay, let's just check it anyway. I did a bit already, but so 3 times 2 plus 2 is 8. 4 times 2, 8 plus -7, it gives you 1. 2 times 1 equals 2, minus 1 gives me 1. So, perfect. It works just fine. So if that's the case, let's look for the third row. I times it by 2 and add to R2. So third row is here, one leading coefficient 1 in the third column. So times that by 2 and add it to the second row as instructed. And that's your answer. Okay, so yeah, okay, I don't know why I got stuck with this question there. Anywho, but yeah, so nothing new. So, but just get comfortable with it if you're not. And this is pretty elementary so far. So let's go ahead and proceed to question 9. This is question 9, A and B. I mean, we've sort of did this already in 1.4, so this seems more like a review, but nonetheless, let's just go through it. So these are the 2 questions. They gave you the matrix A. This is for this is for A and this is for B. I don't know why it has to should be equal sign, but nonetheless, yeah. So all we're really trying to figure out is use inversion algorithm to find A -1, A inverse A if it exists, right? So the thing, so again, there is, okay, it's not a review then. So this is where we get a taste of inverse algorithm, right? So, I mean, so let's see if the inverse does exist first, right? 2 by 2 matrix, there is a really cool way for us to check whether it is inversible or not, right? So we just use a formula that we had, right? AD minus BC, which happens to be the determinant. This guy is the determinant, okay? Not the whole thing. Do not get confused, right? So then it's going to be DA, so A and D flips, and then the sign changes for B and C, right? So we don't really care about this so much. Right now we just want to test if it's inversible or not, right? So AD, that's going to be 7, minus 2 times 4 is 6. So 1 divided by 1. That's going to be just fine, right? Let's look at this one though, just to be sure. So it's going to be AD, so 16 minus 16. Oh, wait. Yeah, because it's minus times minus, so it's, yeah. So if that's the case, what do we get? We have a determinant of 0, which means we have to do 1 over 0 times whatever matrix is. I don't really care what this new matrix is, because you have to times it by 1 over 0, which is undefined, or if you take calculus, really big number, right? So this one I know is not going to be inversible, this one's inversible, right? So if it's 2 by 2 matrix, that's what I would do. But unfortunately, we can't use these methods because we have to use inverse algorithm. So it has to be a little bit more general, which actually isn't all that useless because later on when we try to inverse 3 by 3 matrices, 4 by 4, and even beyond, right? We don't have a nice formula like this where for us to experiment with. So we need a better method, more general method for a variety of matrices with different dimensions. So this is what we do. So what we're going to do is we're going to copy down the matrices. This is an inversion algorithm, by the way. This is tactic. Put a slash in between. You don't have to, but it just gives you a distinction. This is going to be the A. Then this, you're going to put identity matrix. Identity matrix will change depending on what depending on the size of the matrix you're working with. So this is 2 by 2. That's why it's 1 0 0 1. If I was dealing with 3 by 3 matrices, and so yeah, it should be crossed. Then my matrix, identity matrix will be 3 by 3. So it will be 1 0 0 0 1 0 0 0 1. Right? So, and if it's 4 by 4, the pattern continues, right? So I would really doubt that we're going to be tested with 5 dimensions. 4, okay, I can see that happening, but 5, 6, it just becomes really redundant, right? So, but who knows, right? So, to be warned. But anyways, I wouldn't do that. I'm a jerk, so but anyway, so let's go focus on the problem. So you have this. So the goal here is to make changes so that the left side becomes an identity matrix, right? So how do we? Oh, not identity matrix, but not identity matrix, but reduce it as much as possible, right? Oh crap. No, wait. Oh crap, was it reduced? Or did it have to be identity matrix? I think it has to be reduced because you may not get an identity matrix. Yeah, okay, so reduce this as much as possible, right? Then whatever changes you made with the elementary matrix, identity matrix, that will be your new inverse function, right? So let's try doing that. But 1, 4, 2, 7. So again, I like this to be a leading coefficient. Don't want to. It's I'm competing my leading coefficient. So what I'm gonna do is times this first row by 2, and then get rid of it. So this is what you're gonna show. It's gonna be row 1, -2, plus R2 gives me R2. So if that's the case, then this is gonna be 0. And this one's going to be 4 times -8. -2 is -8. That's going to be -1. Okay, so that's going to be... Okay, so first row stays the same. Second row has affected. So here, you see here, right? -2 R1, right? So first row times -2, that's -2 and 0, right? And then add it to the second row. So there's 0 here, so I'm just going to add it to 0. This 0 plus 1. So this is what's happening, right? And we're constantly changing this until this becomes, I think when this becomes identity matrix. I think that's the goal. But it could be reduced. But let's keep going and see the answer, right? So if you do this, and then it's going to be, what I'm going to do is I'm going to do 1, 4, I don't know. So basically, now you have an option. You can switch this into a positive 1, and then use that to get rid of the 4, or you could use this to get rid of the 4 now, and then change this back. I'm going to change this right away because you're going to have to do it anyway, right? So this is second row is as simplified as possible. So it's going to be 0, 1, then it's going to be 1, 0, and then that -2 is going to become positive 2. And this is going to be -1. So all I did was second row times negative gives me the new second row. Okay, so next what I'm going to do is get rid of the 4, right? 1, 0, 0, 1. In this case it's identity matrix, but I'm not sure if that's always the case for other bigger, more complicated dimensions. We will find out the truth when we do question 13 to 15, but nonetheless. So it's going to be what did I do? I did R2 times 4 negative, right? Because -4 times 1, yeah. So if that's the case, then it's going to row 2 will stay the same, and then the first row will be affected, right? So -4, yeah. So 1 becomes a new 1. So let's see, 2 times 4 is -8, -7, -4 times -1 is 4, 4. So, now that I've achieved identity matrix or reduced matrix, so again, we'll figure it out. But the point is, this is as simplified as possible. Now we have this weird looking function. This is your inverse. So I'm gonna write here. Oh, okay, so yeah, that's the idea. I'm actually gonna write the answer here, so that we can check. But anyways, yeah, that's the idea, right? So that will be our new inverse. So don't just circle this. Just say A inverse equals 2, -7, 4, 2, -1. That's all there is, right? I'll tell you why I'm leaving this later. If I can, I want to do checking. What do I mean by checking? What I mean by checking is we're going to use the old inverse formula for 2 by 2 dimensions. It should give me the same answer. But anyways, let's get to this first, right? So B, we know it's not inversible because we checked it, right? But because we're technically not supposed to use that method, let's do the same thing as we've been doing before. So I'm going to put 2, -4, -4, 8. I'm going to put the identity matrix. Okay, so let's actually, yeah, let's divide both of them so that it becomes a simpler number. we see some dangers here, right? It could be inconsistent or infinite solutions or whatever. Oh, no, that's... yeah, that's gonna change. So that's gonna be... do I want to do this? Because I'm introducing... okay, you know what? Let's not do that. Because I thought it would be simplifying would be great, but that may complicate this, right? So let's just do the simplification to the very end, right? So what I'm gonna do is I'm gonna get rid of that 4. So that's gonna be 2, negative 4, 1, 0. 2 times 2 is 4. So what I'm gonna do is 2, first row plus row 2 gives me the new row 2. So if that's the case, 2 times 2 is 4, negative 4, 0. 2 times negative 8, 8, 0. And then this is gonna be 2, 1. Okay? Now, interestingly though, so when we get this, 0 and 0, right? So row 0 was obtained on the left side. Whenever you see this, either on the second row or first row or whatever, almost like when you're, it's almost like as if you were getting infinite solutions, right? 0 equals to 0, right? This has nothing to do with this. These are two separate matrices, if you will. So don't confuse by thinking 0 and 0 will give you a constant of 2 and 1, right? So that's not what's happening here, right? But if you have this 0 rows, that means it's not inversible. That's the key, right? It's like dividing by 1 over 0 from the other method, right? So this tells us that it is not inversible. Okay, so now we could just say, I don't know, you could just say something like A does not exist because A is not invertible or whatever, right? Alright, so I am going to just skip to the next question if you don't want, just because I like to prove things. I'm going to prove that this inversion works. Well, not prove it, but I will provide a good example. What's the opposite word of counterexample? Okay, I don't care. Alright, so it's going to be 7 minus 6. It's going to be 7, 1, negative 4, negative 2. That's going to be 1 over 1. 7, negative 4, negative 1. 1 times anything is just the same thing. This happens to be the same as this guy. So, this looks like a good sign to me, but nonetheless. So that is 9. We're gonna be using this inversion algorithm and push it so that we can solve questions involving with 3x3 matrices. Oh, I almost forgot to post. This is the solution for 10a. I don't feel it's necessary, but just in case, for peace of mind. So this is the steps I took based on what we did in question 9. But again, you can just use the old algorithm, the old inverse formula for 2x2 matrices, just to check your answers, right? I wonder if I could post this. Technically, if you have a graphic calculator, there is a way where you can do simple inverse multiplication of matrices using a graphic calculator. I'm not sure if I should be mentioning that. Alright, well, I will debate on whether I should post that information or not, while you guys, do your own darties to find out what the hell am I talking about. Or for those people who already know, but haven't really thought about it, well, I guess I'll find out on the next quiz if I see you guys doing this then. But do not, whatever method that I may or may not talk about, do not rely on it, because that only works for simple multiplication and inversions, right? When the equation gets more complicated, your calculator becomes useless. Well, not useless, but So anyway, moving on to 13. So this is the long overdue question 13. Alright, so this is a question. This is not on the question, but I just wrote it ahead because we'll be using an inverse algorithm anyway, and we've talked about the process from question 9. So yeah, so this is what I have. So let's do eliminations to get rid of all these annoying competitors. So there's a 1 here. I want that to be leading coefficient. So I did negative row 1 plus R3 so that the new third row is made. So 1 minus 1, get rid of it. 0 doesn't affect anything, so it stays the same. 1, negative of 1 plus not 0 will be negative 1. So, and then you make the same change on this side, right? Should be unique. It's almost like equal sign, right? Whatever you do on this side, you must do the same on the other side, right? So all I did was first row, negative, and then put it up there, right? So this is what I have. And then what I did was, now that this is gone, now I want to get rid of these competitors, right? So I decided to make the new third row, get rid of this using that. So just times it by negative, so negative 1 plus 1 is 0. Negative 1 plus negative 1 is going to be negative 2. And I made the same changes, right? 0 doesn't affect anything. Here, negative, so negative 1, 0 is going to be negative 1. 0 doesn't affect anything, so there you go. So that's that, right? So we are going to keep going. Actually, no, I can just read what I wrote. So then after that, what I did was, it's going to be 1, 0, 1, 0, 1, 1, 0, 0, 1. So for people who are just watching rather than writing down, don't panic. All I did was there was a negative 2 here, right? So I just divided by negative 2 to get a nice leading coefficient of 1 there. So let's see, 1, 0, 0, 0, 1, 0, and 1 half, 1 half, negative 1 half. So that's that. And that was just the row 3 divided by negative 1 over half, giving me a new row 3. So we're getting very close. So I just want to get rid of these two competitors for the leading coefficient on the third row. I am gonna be 1, 0, 0, 0, 1, 0, 0, 0, 1. I can just predict right now because it's 1, 1, 1, so I can get rid of all the ones. Maybe not the best, not a good habit, but you know, whatever. Third row is unaffected, so it stays the same. So I subtract. So what I did was negative R3, negative R3 plus R1 plus R2 gives me the new R1 and R2. So that's gonna be, let's see, so that's gonna be negative, so that's gonna be 1 over half, and that's gonna be negative 1 over half. This one's gonna be negative 1 over half. That's gonna be half. Because there's 1 negative. Oh no, that's negative. So that's positive and positive. And that's the answer. Now, how would you bother to check this? And this was painfully realized on our first quiz. Good thing I took this measures because I made a mistake. So I used this method and then there was a mistake, so I fixed it and got 4 marks. So basically, what I would do, since this is the inversed a, right, or inverse function, right? So remember this we learned in 1.3 and 1.4, right? You have the a times a inverse will always give you an identity matrix, or either way around. It really doesn't matter, right? It will give you identity matrix, right? So based on what we know of that, right, we can say, well, I'm gonna do 1 half, negative 1 half, 1 half, 1 half, negative 1 half, 1 half, 1 half, and then negative 1 half, 1 half. So this is the inverted version, right? Where's the original function? This guy, right? 1, 0, 1, 0, 1, 1, 0, 0, 1. If I times them together, I better get the identity matrix. If you get it, you're solid. If you're not, then if you haven't got this, then you made a mistake. So go back and go through these. Fortunately, this requires very little steps, but for other matrices, especially 4x4 matrices or more, nightmare. Huge nightmare. But anyways, so let's try doing 14. 14 will be very interesting because it requires you to be very, very competent in algebraic processes because they have square roots. Not all of us like square roots. It terrifies most of us. So let's see. So it's gonna be alright. So proceeding to question 14. This one's a little bit tricky because we're dealing with some weird square root numbers, but it should be the same idea. So cautiously approach. If you're comfortable with square roots, then knock yourself out. But for those people who may not be so savvy with these things. So anyways, so we start with this question. I put the identity matrix on the right already. So here, the first step, what I did was I noticed that technically since the base is the same, right? Square root 2, square root 2. All I have to do is just times by 4, and it's going to be 4 square root 2, and that will be the polar opposite of negative 4 square root 2, so that will cancel each other out. So what I did was I got the first row, times it by 4, and added to the second row, right? So 4 square root 2 minus 4 square root 2, that will give me 0. 3 times 4 is 12. 12 square root of 2 plus 1 square root of 2 will give me 13 square root over 2. Be careful. Just because nothing's written up there doesn't mean it's 0. Square root of 2, if there's nothing nothing written before the square root, it's implied as times by 1. If it was 0, 0 times anything is 0, so there should be 0, but it's not. So assume there is 1 in front for those who are not comfortable with roots. But that's that. 0 doesn't affect anything, so it stays the same. I made the same appropriate changes here. So first row, 4, add up to second row. Nothing else is affected, so there's that. So next part is where I was trying to be a little too clever. So I suggest that you divide it into multiple steps if you're not comfortable doing this on your own. Basically, what I found out was, okay, eliminating this using this is a similar idea as this guy, right? But I can only do that simple calculation because it was a simple square root of 2, right? Can I make this simple square root of 2 so that I can do the same thing with this guy, right? And the way to make the simple square root is to get rid of the 13. So divide it by 13. But then rather than just dividing the 13 and then go to the next step to say, by saying negative, so now that 13 is gone, times that by negative 3 to the square root of 2, and these two will cancel out. I sort of did both at the same time. So divide by 3 and times it by negative 3, which will give you negative 3 square root 2. These two will cancel out through additions, right? So this is what I did. Negative 3 divided by 13 times second row, and add it to the first row. So if you do that, if I times this number with this, it will give me negative 3 square root 2, cancels out 0. 0, 0 doesn't really affect anything. Haven't touched the third row, so it stays the same, right? But again, just be careful though, because you don't want to make mistakes, right? So if you're not comfortable with it, instead of doing this, just divide the second row by 13 to get square root of 2, and then on the next step times it by negative 3, and then because why take the risk if you're not comfortable with it, right? So anyways, so that's just what I did. I'll let you decide which method is more comfortable for you. But nonetheless, after this, I wanted to get rid of the square root of 2 because it's an eyesore. So I divide this by square root of 2 and divide this row by the square root of 2. So I have 1, 13. This is where it gets a little tricky, but same idea. Just divide by square root of 2, so it's going to be square root of 2, square root of 2, square root of 2, square root of 2, right? So that's all there is. Now, what I did afterwards is that it's really simple. I just want to get rid of 13, right? I want that to be a 1. I just reduce the matrix, right? So it's going to be 0, 0, 0, 0, 1, 0, 0, 0, 1. And then the first row I haven't touched anything, so it stays the same. This one I did touch, because 13 to 1, so divide by 13, right? So it's going to be 4 divided by 13 square root of 2, 1 divided by 13 square root over 2, 0, 0, 0, 1. Right? So just divide both by 13, right? Okay, so that's the, and 1 over 13, row 2, give me row 2. Okay, so now that I've achieved it, this will be my identity. this would be my inverse of the original function, right? Now, I would totally check this, especially with square roots. So let me show you how you would check it. Actually, no, we already talked about it, right? So get this. So because a square inverse equals to identity matrix, so this. The order doesn't really matter in this situation, but whatever. Let's see. Where's the question? Oh yeah. So it's gonna look like 2, 3, 0, negative 4 squared 2, 2, 0, 0, 0, 1. That will be the inverse. I already tried multiplying this and it was accelerating because a lot of machines were running at the same time. But what actually happens is this actually does give me, believe it or not, the matrix, identity matrix. It would be a fun challenge if you have time to check it for yourself, but it works. Times 3, so square root 2 will be cancelled out, 1 over 13. So 3 times 4 will give you 12. Square root will cancel out, 12 over 13 and 1 over 13. Add them together, you have what? Wait, what? Hang on a sec. Oh yeah, exactly. We're trying to get 1. I was trying to get to the original. No, that was silly. So yeah, so 1 over 13, and you have 12 over 13. Add them together, 13 over 13, which happens to be 1. That, right? And I actually checked all of them just to be sure. But if you multiply them all out, and then you're gonna get this beautiful identity matrix. So that's that. This is question 15. So started off with this. Again, the same thing. Process that we've been doing for 13, 14, and so forth. So first one, don't want the competitors. Get rid of all this 2 with the first row. Okay, just follow through. Add this, and it will be fine, right? Just times this first row by -1 to get rid of all the competitors. And then the second, so I have the second row with only 1 leading coefficient, so I'm going to be using this to get rid of this one. So just times negative, second row times negative, and out to the third row to get rid of this. And then to get rid of that ISO of 6, I got this, and the second row times it by -6 and add it to that one. So that's that, right? So we're awfully close, right? So then all I did was got the first row and divided by 2. Do I want to rewrite this? Might as well. So I have 1 0 0 0 1 0 0 0 1. That's gonna be 70203, because 6 divided by 2 is 3, right? And the rest of them stays the same. So that will be this. Okay, so that's all there is to it for 15. And this is question 20A. The format was really nicely done, so that we can solve this really easily. But anyway, so this is the original function, put an identity matrix, and then I just didn't want the k's, but there's only leading coefficient of k's, right? Can I say leading coefficient if it's not a coefficient? But anyways, so because if I divide this by k1, it's not going to affect anything else anyway, right? So might as well just get that ISO out of the way, right? So I just, the thing is, you have to be careful. Do not just say row 1, row 2, row 3, row 4, all divided by k. There is no k. There is k1, k2, k3, k4. So despite my laziness, on a test, you should be writing all of them, right? So row 1 times 1 over k1 is the new R1. Row 2 times 1 over k2 will give you the row 2, and so on and so on, right? But do not put a generic k. I mean, that would have been nice, and that would have worked if they were all k's, but they're all different, unique unknowns, so can't do that. So, but nonetheless, you can do that, and then just make sure you do the same on this side, so, you know, divide by our k1, so divide by k1, k2, k3, k4. This looks like a k cube. I apologize. I think I'm getting tired and the laziness is getting the better of me. But that's k3, k4. So I have that, right? Notice that this goes like one leading coefficient. It's like the identity matrix, but it's the reverse, right? So 1, 2, 3, 4, like that. So what if this guy goes here, and this guy goes there, and this guy goes here, and this guy goes there? You know. So and that's essentially what I did. So I changed the row. So row 1, row 4 will flip. Row 2 and row 3 will flip, as shown here. And then if I do that, I get a nice identity matrix. So this guy must be the inverse. Now, that's good, and that's good at all. But, yeah. So, yeah, actually, no, I thought we have to identify K1, K2, K3, K4 now. The whole point was assuming that, oh, yeah, big thing, crap. Yeah, I almost forgot. This is it's implied on the question, so I don't think we have to write it. But still, technically, this, and then you put a fat comma and says when K1, K2, K3, and K4 are not 0. Now, why 0? Because 1 over K1, 1 over K2, 1 over K3, 1 over K4. This becomes not undefinable if there are any one of them are 0. So the question already implied said the statement. So I guess it's not the end of the world if you don't write it, but technically you should. All right, and this is 20B. It's a lot of writing, but the kind of writing you might see in horror movies. But yeah, actually, yeah, that's a pretty horrible thing to say. So when you see like people are like writing weird numbers on the wall, either they're haunted or possessed by demons, or the other thing is they're just trying to do the linear algebra. That was not a very fun joke, but nonetheless. So we start with this. It's daunting, but it's actually pretty simple. Okay, just bear along with me, right? So I know. So this is the original function, identity function, identity. What am I saying? Or this is the given matrix, and this is identity matrix. What I noticed is, well, like you can't really cancel out k using 1 or something like that. It's just gonna make the algebra expression more complicated, right? But what I figured out is, wait a minute, there's only one k. I can make this into 1 and then use that to get rid of this one. I wasn't sure what to do with these, but then and the inspiration blew over me as I solved through. But let's go one at a time, right? So I wanted to make that k equal to 1. So I did that by just dividing by k. So that becomes 1. 1 divided by k is going to be that, right? So now that I have 1 and 1, I can get rid of this annoying leading coefficient. And I did so just by getting get the first row times by -1 and then add to the second row. Man, okay. Hopefully you can just hear me because I did not want to write those down. Otherwise I have to write this, erase, write, erase, so basically, so just hopefully you can follow through, okay? So I'm just gonna write it here, right? So it's gonna be R1 plus R2 will give me the new R2. So yeah. So anyway, so yeah. So that's what I did to cancel this one out, right? So wait. Yeah, exactly. So I canceled that out. So only k remains. So this gets a little bit weird, but you'll see a predictable pattern, right? So subtract that, it will be. Oh no, I went ahead of myself. 0 minus 1 is going to be just 1. 0, sorry, what am I saying? Negative times 0 plus 1 is going to be 1 anyway. So yeah. So anyway, so using this step, I'll go from here to here. Okay. Now I have the k by itself on the second row, which means I can do exactly what I did earlier, right? So what I'm going to do is just get the second row. Oops, 1 over. Okay, second row gives me the new row 2. And if I divide it, I get that, right? Nothing else has changed. All this though is gonna change though. 1 minus k divided by k is gonna be 1 divided by k squared. If there was 1 here, divided by k is 1 over k. You'll see the pattern soon enough. But okay, so I have leading coefficient here, I have leading coefficient here. Hey, I can use this leading coefficient to get rid of this. So what I did before with the first and second row, I'm just going to repeat with this to this step, and then I'm going to repeat that step to this step, and I'm just going to keep going until all k's are eliminated, so to speak, right? So then I'm just going to do the same thing. Okay, so then it's going to be, so row 2 minus plus row 3 gives me the new row 3. Right? So then if that's the case, these coefficient cancels out, so you're going to have the k by itself, and then again what you're going to do is k 1 divided by k times 3 gives me the new 3. Right? So see what happens here though? So every time when we go, one step at a time, so cancel out the 1 here, so there's only 1 k left, divide by k, so I'm going to have 1 over k third, negative 1 over k squared, 1 over k, in case if you have a hard time reading this, hopefully you can read it. But you see the pattern here, right? So here there's 1 positive, negative, right? My final solutions, well, not final solution yet, but it's going to be positive, negative, and you'll appreciate the pattern soon enough. But you can use a pattern, not necessarily to cheat your way through, you could, but mostly just so that, you know, oh wait, like am I on track? Pattern's predictable, so if I screw it up, the pattern would break. And if the pattern breaks, that means I did something wrong, right? So essentially, and basically I'm just keep repeating the steps, and I haven't quite finished it yet, but I'm almost there, right? K remaining, right? So all I'm gonna do now, so hopefully you can just follow through, because the pattern that I just told you is basically just repeats itself. Oh no. Nope, that's kind of positive. So, because it's negative 1 over k to the power of third, so if you divide k here, you have to divide here as well. So it's going to be negative k4. So divide everything by k again. So that's going to be k. Okay, and that will be the inverse. Yeah, this is one of the questions where I wouldn't really bother double checking, but you know, you could, right? So that will be the new inverse, right? Again, I'm too lazy to do it now, but make sure if you're answering it, make sure you say that this function, so I think it was a, that's what it was called, but let's say it was a, right? Then copy and paste this on here. Just don't leave it like this and say, this is my inverse function, right? So, no. Just technicalities, right? So that's 20b. Okay, so this is 21. This same idea, just the only thing that might throw you off a little is if it's the fact that they use unknown variable, well, not unknown variables, is they're using like variable rather than number to, yeah, I guess you could say unknown variable, yeah, but so they're using variables rather than numbers as entries, entries for the matrix, and that might throw some people off. But it's the same idea, and we'll figure out why it's the same idea. Anyways, this is the original matrix identity function, the usual, right? So here all I did was I got the first row and the third row switched, just so that I have a leading coefficient on top here, right? It doesn't have to be here, you could just use this, but you know, that's what I did, right? I like this one, right? So I did that, and basically this, and what I did was, well, I gotta get rid of the competitors, right? So 1 and 1, what do? I just get the first row, times it by negative, that should cancel out that, right? So negative row 1 plus row 2 gives me row 2. This, you might have to think about a little bit. I was wondering, it's like, how do you use a number to get rid of a variable? And I realized, oh, you could just times it by the variable. So 1 times negative c will give me negative c, plus c will cancel those out, and leaving a 0. So I just said negative c times row 1 plus, and add it to row 3 will give me the new row 3. So I just did that. So 1 times c is 1 times negative c is negative c plus positive c is 0. Same idea here. So c times negative c is going to be negative c squared. And then there's a c here, so c minus negative c squared. And I made the same appropriate changes for the identity matrices as well, right? So I've done that. So basically remember, the question for this was, and did I drop a question? Oh no. So the question of this is, find all values of c where the matrix is invertible. Yeah. So basically when that happens, remember what was a condition for invertible matrices? It was any rows that had on the identity, any rows that has 0 rows, right, at the reduced form. So 0 equals 0. So that would be a sign where it says it will be invertible, right? Just like we can't divide 1 over 0 in the 2 by 2 matrix formula, right? So because of that, well, I mean 1c, it can never be 0, right? So we don't have to worry about that, right? So because there are too many variables. This one, there's a one variable, c minus 1 could become 0, right? So we're going to have to test it out. So I put c minus 1 equals 0. Another one, telling one is this one. C minus c squared will give you some kind of 0. So I wrote both of these conditions. Because if one of these happens, then, it's not going to be invertible. So let's start with this one. So I actually just factored this one out by c. So it's c times 1 minus c. If you're not sure, just times them together, and this should equal to that, right? So I have this, right? So when I factored it out, let's see, 1 minus something, so either c has to be 0 or 1 minus c has to be 0 for it to be 0, right? Well, if c is 0, 0 times anything is 0, so 0 can't be it. 1 minus something cannot be 0. What? 1, obviously, right? 1 minus 1 is 0. So 1 or 0. That's what I said, right? So as long as c doesn't equal to 1 or 0, we can invert this. But if we can't do that, then so if actually becomes equal, then a minus, or is that a? Let's say this matrix was a, right? Then that does not exist. Now I tried doing this at first, but the prof that I was talking with said maybe this is not the best way to show it. So what I actually did at first was, instead of factoring it out, I just said, well, c equals c squared, because I'm just moving the c squared to the other side. Okay, then all I'm going to do is I'm going to square root those two. So if I do that, it's going to be c equals to square root of c. Right? So if that's the case, then, what's the only numbers can you think of where these two will equal? If c's are 0, square root of 0 is 0, so 0 and c will be 0, so if 0, 0 will work. If I put 1, it will work, because square root of 1 is 1, right? Now, apart from 0 and 1, what is the other possibilities? Right? Let's say we put 2. This will never happen. This will never happen. This will never happen, right? So because of that, we're pretty close. The only problem with this is, technically I could be saying this, because of the nature, right? So if I do this, it's going to be c, oh, no, that's technically, that may not be true. Right? Because, yeah, because it could be plus or, crap, that's why, okay. Yeah, so this gets, so if you square root something, it's going to be positive, negative. So technically we could say -1 cannot equal to -1. But that's where it gets a little bit convoluted, right? So it's better to just have this, because it's more clear, where this is, you have to worry about positive, negative. So don't fall for this trap, right? Now, some people might ask, well, like, you check for this function, this restriction, fine. You haven't checked this restriction. I just didn't bother because it's the same thing, right? C minus 1 cannot be 0, so when is that possible? It's going to be just C equals to 1. Well, we already have 1 here, so that's why I didn't bother. But, you should be checking for all restrictions. Okay, so this is question 22, the last one. So, for this purpose, for this question, and I should have done this with 21 as well. I didn't bother putting the inverse algorithm, so putting identity matrix on the right, simply because the question is asking whether you can inverse this or not, and rather than trying to find out what the inverse is. So I just want to, I just skip that step, and basically I'm just reducing it until I see any row that has a close possibility of 0 equals to 0, right? So let's proceed. So we have this, and original one, and basically I just flip the second row with the first row just to have that leading coefficient right on top left. And then I want to get rid of that competitor, so I just times the first row by negative c, which cancels this one out, but makes this one a little bit ugly, but that's okay. So I have 1 minus c squared, and then negative c, 0 in the first column for the first row. And then what I did was I got the second row, I got the third row, times it by negative 1 and add it to the second row sorry, there was a mistake. I just pointed out. See, that's a good thing that. So, because if I want to do this, I don't want to make it negative. I just want to add it, right? So that's going to be R3. That way, c and negative c will add together and become 0. So that's actually going to be. Yeah, man. Like that. Okay, it's horrible, but this is 1 minus c squared plus 1, right? So you have that. Oh, that's going to make things a little more tricky. Okay, so if that's the case, then this flies out of the window. Yeah, okay, so then I have these two possibilities where 1 minus c squared plus 1 equals to 0, and then 1 plus c equals to 0. Yeah, but that has to be right. Okay, yeah, so if that's the case, this one's easy, right? C can't be, c is negative 1 if you move it, so if this is the case, then it's not inversible, right? Because then you will have a 0 equals 0 situation. This one, however, is a little tricky. Yeah. So we have that because it's 1 and 1 both are positive, so 2 minus c. Okay. So. Oh, no, we can't do that. Okay. Whoa, what am I doing? Jeez. Okay, so you have that because. No, we can. Yeah, we can. This is not a yeah, okay. I thought it was gonna look like this. That's why I was like, oh no, we can't add inside of no, that doesn't matter. So if that's the case, then it's gonna be 2 minus square equals to 0. That means 2 equals to c squared, which means 2 square root is gonna be c plus or minus. Okay, so that I guess that's what it is then. So when c equals to negative 1 or plus or minus square root of 2, then you're gonna have a 0 equals 0 rows, which means those not inversible. Okay, yeah, that's gotta be it. Just trying to make sure that I haven't made any mistakes. Oh, okay. See. Okay, 1 times. Yep, no mistake whatsoever. Pretty sure. Yes. Yeah, I'm pretty sure. So yeah. Anyways, yeah. So that's gonna be the answer. Yeah. So really, so as we've learned, as we went through this section, it's not that hard. You just have. You just use the inverse algorithm and this new restriction rule that we learned about. That's all there is. Yeah. So, anyways, yeah. So, but please be comfortable with it for the next quiz. Or unfortunately for our class, we already got a taste of 1.5 already for the first quiz. So I apologize for not uploading this earlier, but I didn't know. I thought we were being tested until 1.4. Good thing that I did this. Well, I didn't make the video, but I did. The section nonetheless, so I managed to survive the last question on the first quiz. But anywho, But that's that, and I will see you for section 1.6.